What did I even do before? So, hello, I'm Substack. This is me. I'm going to be doing musical things today. So I haven't ever talked about musical things, but I have actually a lot of musical experiments that I've been cooking up passively over forever. So first of all, what is music? What is it really? I mean, in computers, I don't know if you ever had like an old Linux box. You used to be able to do this. It still works if you have like OSS, I think, but with ALSA it doesn't work. Anyways, so audio is just this device that you can write bytes to in some fashion or another. Whether you have to do that through a command or whether you get a nice devfs like block device, it's just bytes. So randomness actually sounds pretty cool. We can't actually run this program, but we can run this program, which is basically the same thing. So first of all, to do any of this, you should install Sox. Sox is amazing. It's just like an audio toolkit for doing anything. Basically, I just pipe bytes to it and play it, and you can also use it for recording from a microphone or doing fancy things. The important part is here we can instruct play to play this dev random device, and that sounds like this. It's just static, white noise. Kind of boring, but it illustrates that if you have a file, you can play it. You don't have to have like an MP3 file or an OGG file. You can just play raw bytes. So in particular, this is using S8, which is like a byte is a value, and that's it. So, and at 44K, if we actually adjust that to be 8K instead of 44K, then it sounds like even more old school retro. This is like the sample rate that is used on really old audio demos and things, like on Amigas or something. Really lo-fi. So what's really cool is instead of a file, you can give the play command a dash. See right here, we've got a little dash at the end. And that says read from standard in. Once you can read from standard in, you can pipe files. So here that's just the same, this is just the same thing as the first one when we specify the file manually, so we get static. But maybe we could do something different. So here's a little bash script that will play basically a square wave at 8K output. So if we play this file, so basically what's happening here is we're writing like all zeros and then all ones for a bit and just alternating that pattern with a while loop in bash. And we can play that, and it sounds like this. So as you can imagine, if we can just write a program to output bytes that is our music, we can make any kind of music with a sufficiently complicated program. So that's what I will be doing. Here's actually one of my first forays into this musical computing idea. This is a Perl script that I wrote in 2006, and I posted it to Perl Monks, actually. Here it is, by Substack, as you can see. And what this program does, if you can't tell, is it plays Mary Had a Little Lamb, but it's kind of offbeat. So basically, like this part right here, this JKLK thing is the payload, and then it uses this formula, which I did incorrectly, with log base 2, which I'll get into in a bit. It's relevant here at the top. And it plays a song, which I've encoded in the data payload. And so we can play that file. Yeah, I was in high school at the time, so it's not very good. But I wrote this module that makes all of this stuff quite a bit simpler. So writing bytes is cool if you're into like bit twiddly things, but it's kind of really hard, and I don't like that as much as writing just floats, because floats are really nice. You can use things like math.sine to compose your audio functions, and it's just much simpler. You can just add the sine waves and multiply the sine waves, and you don't have to like do all of these esoteric demo scene tricks where you're like taking modulus and then you're using like XOR, and it sounds like a thing, and making sawtooth waves based on like rounding errors. I don't know. Yeah, this is much easier. So I've got this module called Bodio, npm install Bodio, and what it does is it lets you give it a function, right, that takes a parameter t. T is time in seconds, and you just return a float between -1 and 1, and the float is the amplitude. So, right, if we just return a sine wave of 2 times pi, like 2 pi times the parameter t in seconds, that'll repeat every second, the sine wave. So if we multiply that by like 400, we'll get a sine wave of 400 hertz, which sounds like this. Neat. So right here, actually, we're just piping to standard out. So you can do that with just the play command. Or Bodio actually has something built in where you can just do b.play if you have socks installed, which just runs the command for you. So same thing, but a little nicer. Right, so that's the basics of like raw audio and how to get it working with just like bash one-liners and such. Let's talk about waves. So sine waves are cool, right? Here's an ASCII sine wave, right? It's kind of like rounded around the corners. This is the same thing as I just played, so hang on. Right, so if I play this file, same thing, boring. One little trick that I often do is tau. You know tau, it's 2 pi. It just makes the math easier because you have 2 pi terms everywhere, so you can factor that out. You can also like factor out the t parameter because all of these functions are going to take a parameter t, and you can just like write a closure for that. So here we can just have sine of 400, which gives us a sine wave at 400 hertz, which sounds like the same as the last thing. It's kind of boring. Yeah, exciting. Here's something cool you can do. So if you take the sum of 2 sine waves, an interesting thing happens if the frequencies are really close together. So here we have a sine wave of 400 hertz, and we add that to a sine wave of 100 hertz. Now, they're mostly going to be constructively interfering at first, right? They're going to be just adding the values together. But every second, because one is at 400 hertz and one is at 401 hertz, so the difference is 1 hertz, or once a second. Every second, the second wave will catch up completely with the first wave, and they'll cancel each other out. So you get this fading pattern every second with this example where it fades in and out every second. So if I run that, that's once a second. We can make that a little faster if we want. So here's a difference of 4 hertz. Or even faster. This is 5 hertz, or 8 hertz. Okay, so now we're getting into something a little more interesting. We can also do square waves. So square waves, I've got an ASCII image of that. They're like sine waves, but boxier, I guess. So here we've got a square wave, and basically this just takes the sine wave and returns -1 or 1, based on which side of the 0 you're on. So if we run this example, you can... So here I'll run the sine wave first. That's the sine wave, and this is a square wave. So it's much louder, first of all. That's because like it's spending much more time at the poles, kind of the equation. So it's like top lining and bottom lining it. So it's louder, first of all, but it's just kind of gives it a different timbre. You can get these constructed patterns with square waves too, and it gives a similar kind of effect, but it's a little bit different. Hang on. Okay, maybe not. I guess that is different, but yeah, anyways. You can also do sawtooth waves. These waves look like this. They're like little triangles. So you start at the bottom and you go up, and then you fall back down and you go up. And these just have a different timbre again. These are kind of like the base primitives that I write a lot of this stuff in. So sounds kind of like, I guess, sharper, shriller, I guess, if you want that. It's good for cutting through bass sounds. Like if you have a lot of bass and you need to just slice through that, just throw a sawtooth in there. And you can also like constructively interfere these things, which sounds kind of neat. Go faster. Yeah. So you can also just mix and match waves. So here I've got a sine wave and a square wave and a sawtooth wave, and they should like interfere in some neat pattern. The cool thing is, because this stuff is really subjective, you can kind of just guess and test your way into these awesome sounds, and so kind of build the pieces out incrementally without knowing really too much what you're doing, just kind of like making good guesses and sticking with it. So anyways, let's talk about sine waves a little more. Here I've got just a basic example that we started with, the sine of 400. Another thing you can do is multiply sine waves together, and this gives you a neat like fading effect too. So here every second the 400 hertz wave is going between being completely silent and then being completely regular volume. This is a neat trick. If you multiply a base sine wave times the sum of multiple sine waves, you actually get this interesting pattern effect that I found is really awesome for beats. So here if we have a sine wave like at 1 hertz and a sine wave at 2 hertz and we add them together, you're going to get a constructive interference pattern every second that repeats itself. And these things like have this neat prime factorization quality that you will hear in just a sec. So here's what this sounds like. So it's doing bam, 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 bam. Can we get it a little louder actually? That'd be awesome. Okay, so here we've got just some other sine waves. This is just a Pythagorean triple, why not? Just a 3, 4, 5. So here's our base wave, and then we've got it's basically just a more complicated pattern. And you can use whatever terms you want to get like crazier and crazier complicated patterns. And you could use floats, you don't have to use integers. But the nice thing about integers is they repeat faster, or they just, I don't know, the math is easier. So that's a neat trick, right? You can also do this with square waves, of course. So here I've got a square wave. We can run that. It's a little louder. All right, we're almost making music a little bit, and we can try the same thing with Sawtooth. And you don't have to use sine waves either. When you multiply the sums of waves, you could use whatever you want. So here is what it sounds like if you have a sawtooth times a sum of sawtooths. Cool. So that's neat. Here's another trick that you can pull with sine waves. So right here, here's like how you can compose once you've made these little patterns. How you can start to compose them into multiple patterns. So here we've got just a 200 hertz wave. It's pretty low. And here's a higher one. Now what if we want these both to play together? Well, that's really easy. You just sum them. And you don't have to always divide by 2, but this just makes sure that the values are not going to clip, because if you get too much clipping, you can hear it. And sometimes it's kind of cool because it turns it into more like a square wave, but sometimes it just makes it sound crappy. So yeah, we've got the low sound and the high sound at the same time. Another way to write this, so we can do the same thing with adding these different effects like this. So here we've got the low sound, but we've got the high sound times the sum of 2 sine waves. So that'll give us like a pattern on the high end and then a low bass sound that just plays by itself. And we can add a pattern to the low sound too. So here we've got the low sound, and that's just on a slightly different pattern. Neat. So if we want a melody, here's a neat trick for doing melodies. So the Pythagoreans, they probably somebody else probably figured it out, but they were the first ones to talk about it, so it's kind of considered their idea. Anyways, the Pythagoreans discovered that if you take a string, like from a stringed instrument, and you pluck it, you obviously get a sound. And if you cut it in half, you get a sound that is exactly 1 octave higher. And you can keep doing this, cutting it in half, and keep getting an octave every time. And that's sort of how your brain is processing sounds, right? So the cool thing about that is you don't just have to take an integral amount of like cutting in half. You actually take fractional amounts of cutting in half. To do this, you can just take like a whole number ratio. Works really well and sounds really awesome. Basically any whole number ratio or any kind of pattern So long as you take it to like 2 to your ratio, it's going to sound awesome. So here I just made up this is like the first thing that I just made up, just a bunch of fractional ratios. And if you take those like 2 to the power of that times a base frequency, so in this case 400 hertz, it sounds like this. We can make a little melody. So that's just a sine wave, which isn't too interesting, but at least we've got this melodic pattern going on. We can, of course, make this more complicated. So here I've got a sine wave times the melody plus a square wave times the melody at a little bit higher base frequency, and then that plus a sawtooth wave. So that'll give us just a more interesting kind of timbre to our musical melody here. And we can also punctuate that with a pattern. So here I've got the sum of 2 square waves. So this will give us like a da-da-da-da or something. I don't actually remember. So let's play it. Whoa. So you can punctuate it a little bit, which is fun. Another fun thing to do is to use little Boolean expressions all over the place. So if you just multiply by well, here's just a ternary expression. Another trick is to multiply by, or just to add a Boolean expression times the quantity when you want to turn something off and on again, because the Boolean will coerce itself into 0 or 1, which is handy. I used to do that TI basic programming with like making silly graphs and things. You just stitch together the pieces with Boolean expressions. Anyways, so if we have something like this, we can switch between like a sine wave plus a square wave and just like 2 square waves, which sounds kind of neat. So we can change the instrument kind of on the fly. So every 2 seconds, the instrument is changing. So that's really kind of all that you really need to know about waves and stuff. I mean, sure, there's more, but you can get really far with just these simple ideas. But let's take a brief detour and play around with this little keyboard I've got. So thanks, Nexi, for letting me borrow this. So I wrote this module called asynth that uses Bodio to do the same kind of stuff. So basically with asynth, you write a function that takes 2 parameters now. It takes the note, which is just an integer, like it's the integer index of the key that you press, and it takes the time and t parameter, just like Bodio. So once we have this kind of a thing, we can just return, so you can look up on Wikipedia this algorithm, or this little formula for determining what the frequency of a note should be based on its index, and it's that. So just copy-paste that, and just return a simple little sine function here. So hang on. Oh, aha. Okay, so here, and we can play multiple notes at once, and asynth figures that out. Neat, so we can make our own synthesizers with like little one-liners. Awesome. Here's a more complicated one. This one is like an organy sound. Basically, it's just a couple of sine waves at different mixer levels, all summed together. Sounds like this. Neat. And here's something a little sillier. This one is kind of like a warbly sound. It just fades in and out using one of those syncopated pattern tricks. If we play this, we get... And then, this one is crazy. I was trying to make a delay pedal this one time, but I messed it up. But it sounds awesome, so I just Bob Rossed it, and it was my happy little mistake here. So, okay, let's see. And then it keeps playing itself, because it's like got this little buffer built into it, so... Synthesizers, they're neat. Anyways. So, But now let's get back to our regular scheduled programming. Here I've got another example of actually building something that's more of like a kind of like an original piece built out of little components. So I'm just going to step through this brick by brick. So here we go. This is just playing around. I discovered this neat little way to make a kind of neat effect. It's like wavy. That's all that function does. I don't know why it works. It just does. Guess and test. Okay, so that's cool. Then we can make a little melody, just like using an array and indexing it based on the time parameter t, and then you just take the floor of that. And if you want it faster, you just multiply by a constant. So we can do the same thing with this effect. Yeah, kind of. So we can extend that a little bit with some more maths. I don't even remember what this does, but let's just play it. Let's see. Oh yeah, so this just, instead of directly depending on time, it takes like the sine wave of time in part of it, so it's kind of oscillating. And then if we take that and punctuate it with one of those little sum of sine wave tricks that I was showing you, or that's two of them stuck together, to make a sweet, like, beat. So if we just get even crazier with time, like here I'm just like taking the time and just making it repeat every 8 seconds because it got kind of weird past that. And we do some other tricks like adjusting the speed on the fly to make it faster or slower. So here I've got like a little modulo expression that kind of just like flips the speed around at the 7-second mark, it looks like, something like that. Anyways, let's play it. Oh yeah, that's the warbly bit. You get more volume? Okay, so we've got that, which is cool. We can also add a little tick to it. I forget what this does exactly. Oh yeah. Oh, this is a sweet trick. So if you need just like a really simple beat, math.random, like we saw at the first couple of things I did, gives you like static. But if you guard that with a little ternary expression, you can make like, you can cut the static up and give yourself a simple beat to any little experiment, which is fun. Anyways, so we can delay the offset too with just more guarding the conditionals, which just starts the tick after a bit. Anyways. Then the other part, so using that same effect from the start, I was messing with making a cool, like, more complicated beat. So here's, so here that it's that, and it kind of like goes to static, I think, because of rounding errors over time. So that's what this more complicated version of that random trick is doing. See how I'm doing in time? Okay, I'm gonna go faster. So, and this just like delays the offset, whatever. This is fun. So I've found a way to make like a honking sound. It sounds kind of awesome. Check this out. So let's put a honk in there. Let's punctuate it first of all. Make it sound cooler. Oh yeah, and then we'll add a little ternary expression with regards to time to like cut that to make that only play sporadically, so it's not the whole song. Okay. Hang on. I'll give it a time. There it is. Cool. So that's kind of sweet. Let's very quickly rush through this drop-on-drop stuff. So this is just another one of these examples. I started with actually the same effect for this one. And so here's, right, we've heard that. And then I added this other little thing that just like adjusts the time every now and then. So it kind of was just like adjusting the punctuation on the fly. Then I added this other thing. Yeah, just more kind of neat stuff. And then added a tune to it. So here we've got tune. And if I just jump ahead a bit, more tunes, more stuff, more punctuation. And then, so I'll play that. 2 tunes going at the same time. Now the next part is really cool. This is something I discovered where if you just take the time and rewrite it occasionally, you can actually like cause the whole thing to drop. Like you're just like putting your finger on a record player and just slowing it down and bringing it to a stop. That's what this sounds like. And if we extend that a bit with like a come up and come down, and we put, let's see, if we do this. This is the whole thing, and it's got the drop in it. So the drop is only at 23 seconds. Let's just jump right ahead to that. You can just like start layering this stuff and get so crazy with it. Anyways, very quickly, next thing. This is another example I was working on called Clown Dentistry. Basically, I start with just this really simple sound. It's just solid waves. It's just a couple of sine and sawtooths stuck together. I can extend that with a punctuated pattern, of course, and extend that with like a sum of patterny things. So these are all the same tricks that I was showing in like the wave part. So it's going down, 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 and then extending it. And then if we extend that with just some other random noise, I'll just skip ahead a bit. So here we're punctuating the patterns. Every 7 seconds something cool happens, and right before that we added like a wavy bit. So if I play this, and then if I skip ahead more, I've got like a Yoshi sound in here that I discovered. So here is, let's see, 130. Can we get more audio? Hang on, I can make my own audio. There we go. So here we've got like a boink. That boink, which is fun. Yeah, whatever. Okay. I've also got like this grunge. I just called it grunge. It really isn't, but call it that anyways. Of just like one of those melody patterns of just whole number ratios. And I added that parameter to a couple of the functions just to sort of modulate it with some overarching melody. And then I added this part right here that sounds awesomeness. That's like hyperdrive mode. Anyways, and then drums. So if we put some drums on this thing, like this, then we can just add that into our function down here. So here we've just like plus drums to our whole thing, I think. And we can make the drums fade in, of course, and do a couple of other things. Anyways, and if I run that, oh, and it's all quiet. Hang on. Louder. Okay. So here's the whole thing. It's just a bunch of these little pieces stuck together. So that's cool. But it gets even cooler. You can actually run this stuff completely in the browser without any modifications. So here we're just using Browserify, and there's this module on NPM called Web Audio. It's basically the Audio API, but it works in browsers. So it's really awesome. If we just compile that, that's exactly the file that we were just playing. And now if I open this, give it a sec. Playing a little bit quieter because I didn't boost the sound. I don't know. I think maybe. Who knows? Anyways, so I'm just about out of time. I could freestyle a little bit, but I don't know how we're doing on time. 10 minutes? Oh, fuck yeah. You guys want me to freestyle a bit? Okay. Okay, so here I've got a drum pattern that I already prepared. Just a little audio function, and let's make that louder. That's how you make it louder. Okay. Move the microphone closer to the headphones, of course. Okay, so here I've got just a simple drum pattern because those are kind of hard. So if we factor this out into a drums function, so function drums parameter t, and return drums of t, it's the same thing, right? Cool. So maybe we want a little, I don't know, we'll just put like a simple sine wave in there, right? So sine of, I don't know, 800, right, plus the drums. And then we'll just make a little happy sine handler for us. So return math.sine of tau times n times t, which we get in the closure scope. And if we play this, we should hear like a shrill sine wave. Yeah. Okay, so we've got some drums and we've got a simple sine wave. If we want a simple melody, we can do that. So we'll just define a little array of, I don't know, throw some whole number ratios out. Go. I'm just going to negative 2/3. Okay. Thirds are kind of happy. I don't know that I like thirds very much. 4/7, 5/12. Okay. 27/11. All right. Cool. So if we take this melody, actually we probably want to move this out, and we map it. This is the part that makes it, whatever you just did, sound awesome. If you return math.pow of 2 times to that, it'll just sound good. It doesn't matter what it is. And then if we take the melody parameter, so here we've actually got to take the floor of t and mod that with the length if we want it to repeat. So that'll be 1 note a second, which takes fucking forever, so make it faster. Actually, hang on. Oh, you're right. Yeah, that's what I have to do. Okay, so times m. That would explain it, so let's put that back. Cool. And then sine waves are kind of boring. Let's go steal one of those like sawtooths. Those are pretty sweet from the waves. This one. No. No, where is my waves? Waves. Okay, let's do a sawtooth and a square. Yank. Add them. They are added. And then... Cool. And then let's, I don't know, put some more sounds in there. Actually, let's do this. And then let's add in a square wave of like 400 times m plus 4 to like give us a little bit of constructive interference. And then it's clipping, that's why it's so loud, so we'll divide it by a little bit. And then we can add like another sawtooth in there, or maybe a sine wave. Sine waves are kind of cool for bass stuff, so like at 100 hertz. Let's make that straight up. And we can punctuate a little bit, so let's take like sine of 3 plus sine of 4. Let's give us a little bit of a pattern. We'll do the same thing with square wave with a different pattern, so like sine of 1 plus sine of 2. And then that sine wave kind of, let's make it a square wave. That'll be more of a discrete step instead of something so continuous. And then we can like add more stuff. You know, we can basically do whatever we want here. So I think that's about good for this presentation. So here's some links. This thing that makes it easy to just write to output bytes from floats is called Bodio, and you can check out my SoundCloud. I've posted a lot of these experiments up there. And also the other package is called Web Audio, if you want to check that out. So thanks.